Some of the concepts in here can be quite tricky because they are quite abstract. They're difficult to visualize field lines and so on. But once you get through the questions and work through a lot of them, you realize that the majority of the questions are the same. What is worth knowing is that paper 1 for higher level does seem to have quite a lot of questions. So the multiple choice questions do seem to be heavily examined in paper 1. So it's worth really getting ahead on them. So we'll start with multiple choice questions and then we'll look at some longer questions as well, interspersed as we go along. Question 1. Faraday's law of electromagnetic induction states that the electromotive force induced in a conductor is proportional to, and then we have 4 answers. If we nip to the data booklet, we can see that Faraday's law is, I'm going to use that symbol for E. I've not written it exactly as it is in the data booklet, but this here is magnetic flux linkage. Linkage takes into account the number of coils N. And this section here is the rate of change, how quickly it changes with time. So our answer is the rate of change of magnetic flux linkage. Magnetic flux linkage is when you take a number of coils into account and that N factor is there. A magnet oscillates above a solenoid as shown. We can see that a magnet is suspended on a spring and that's going to go down into the coil and back up again. We know from electromagnetic induction that a current will be induced in the coil and a reading will be shown in the ammeter, and this resistor here is to stop it short circuiting. The question says, a magnet is displaced vertically and released from its highest position at time equals t0. So at t equals 0, it's up here. Which graph shows the variation with time of the current I in the resistor? We're looking for a graph to show what I looks like with time. Now we know at t equals 0, because this magnet is not inside the coil and it's being released from that point, then at t equals 0, current will be 0 as well. All our graphs that are correct will have to start from I equals 0 at t equals 0. But we'll see what the graphs show. The only graph that starts at 0 is A, so the answer is A. Now we have a longer question here. The diagram shows the main features of a loudspeaker. A current carrying coil is positioned within the magnetic field provided by a permanent magnet. We have a permanent magnet. You can see the north and south there, and the north down here. So we have a magnetic field from there to there and a magnetic field from there to there. The diagram also shows the directions of the magnetic field and of the current in the coil at a particular instant. So the top half, the current is leaving, is coming out of the page, and in the bottom half, the current is going into the page. The dust cap D prevents dust from blocking the gap between the cardboard tube and the south pole of the magnet. The coil consists of 150 turns. Let's pop our data. We'll go back to the diagram in a second. N equals 150. Each of average diameter, so the diameter is equal to 0.025 meters. That means the radius of this coil is 0.0125 meters. The magnetic field of the permanent magnet has a strength of B is equal to 0.4 times 10 to the minus 3 Tesla because it's milli. And the peak current in the coil, I, is equal to 0.45 times 10 to the minus 3 amps, again, because that's milli. So we've got our data there. That'll help us with a calculation later on. Question 5a. Identify on the diagram the direction of the force on the coil with the current in the direction shown. We're going to have to use Fleming's left-hand rule here. And Fleming's left-hand rule, left is really important, we use left-hand rule. We have our fingers mutually orthogonal, so they're all perpendicular to each other. The thumb is the direction of the force, and so we're going to find out which direction our thumb is pointing. Our first finger is the direction of the field, magnetic field. And the second finger is the direction of the current. So I'd like you to put your left hand in front of you. I'd like you to put your second finger, let's take the top section here, the top section, and I'd like you to put your second finger pointing up towards you, out of the paper. I'd like you to put your first finger pointing down the way, and what you should notice is that your thumb points in that direction. Now if we check it on the bottom one, now we're looking at the bottom section, I'd like you to put your first finger, which is the field, pointing up the way from the north to south. I'd like you to put your second finger, which is the current, going into the page, pointing into the page. And again, you should notice that your thumb is pointing to the right. In both sections, our thumb points to the right, and we'll pop an arrow saying the force is to the right. Do we have to label it with anything? No, we didn't have to label it. We can write underneath as well. Calculate the maximum magnetic force acting on the coil. So the magnetic force is calculated using BIL sine theta. Sine 90 equals 1. So we've got to pop in our numbers here. B is 0.4 times 10 to the minus 3. I is 0.45 times 10 to the minus 3. And L is the length of the wire. At the moment we've just got the radius of the wire and 150 turns. So we have to do 150 times the circumference of one of the turns. So circumference is 2 pi r. So 2 pi times r is 0.0125. When you pop all those numbers in, we get an answer of 2.1 times 10 to the minus 6 newtons. Question 5c. Explain with reference to electromagnetic induction the effect of the motion of the coil on the current. Okay. So when the coil starts to move to the right, it experiences a change in flux linkage. It crosses some of the magnetic field lines. This induces a current in the coil. That's easy enough. But due to Lenz's law, the direction of current must induce a field, magnetic field, that opposes the change that causes it. Therefore, the current, or the net current, is reduced. Next question, which is about changing magnetic fields. A single turn conducting square coil is released and falls vertically from rest. Falls vertically, so it's going to be free fall due to gravity. That might come into it later. At the instant it is released, the coil is a boundary of region of uniform horizontal magnetic field directed into the plane of the paper shown. The ends of the coil are not joined together. If they're not joined together, that means that no current will be induced as it falls, which means that Lenz's law, we don't have to worry about it just now because no current will be induced. So that's freeing us up from worrying about Lenz's law. Each side of the coil is 0.05 meters long. The dimensions of the magnetic field region are greater than that of the coil. the magnetic field strength is 25 millitesla. So our B is equal to 0.025 teslas, or 25 times 10 to the minus 3 teslas. Calculate the electromotive force induced in the coil at the instant just before the whole of the coil enters the magnetic field. So we want to find the current induced in the coil at this point here, where the whole of the coil enters a magnetic field. That means it's fallen a distance of S equals 0.05 meters. And I think we're going to have to use SUVAT here, because we've seen that it's falling from free fall. We know that the acceleration of that will be A. We know that it falls from rest. So I think that's going to play into this question. But let's just have a look. To calculate the electromotive force, we're going to use Faraday's law, which is the rate of change of magnetic flux linkage. Magnetic flux is given as BA cos theta, and N magnetic flux linkage is given as NBA cos theta. Now we know it's a single coil, so N equals 1, and cos theta, because they're perpendicular to each other, will be 1 as well. What we're really looking at then is equal to the rate of change of BA, because the others are value 1. Now it's said very clearly in the question that it's a uniform horizontal magnetic field. That means that B does not change. Let's go back to here then. E is equal to B, it doesn't change, the rate of change of area with time. So what we're saying is we need to find out a value for the rate of change of area with time and then pop it into there. The rate of change of area. The clue was given that it falls freely. What we want to do is find the speed of the coil at the instant that we're talking about. So we're going to use SUVAT to find that out. By doing so, what we'll find is the rate of change of distance at this point here, and then we'll multiply it by this value here to find the rate of change of area. So we're working on that point there. And let me just expand a little bit on that, because dA by dt is equal to the rate of change of length with time multiplied by the width of the coil. And dL by dt is equal to velocity. It's just a rate of change of displacement with time. So we want to find the velocity of the coil at that point and then multiply it by the width. Velocity of coil, we can use this. So V squared is equal to U squared plus 2AS. That equals to 0. So V is equal to root 2 times 9.81 times 0.05. And that gives us a value of 0.99 meters per second for speed. If we go over to here, is equal to dL by dt, we now know is 0.99 times the width. So dA by dt gives us a value of 0.0495 meters squared per second. And then go back over here is equal to 25 milliteslas, that's B, times 0.0495, which is our dA by dt, which gives us a value of 2.1 times 10 to the minus 3. No, it doesn't. I've done that wrong. 1.23 times 10 to the minus 3 volts. That's our answer there. That's quite a difficult one, actually. I always find if you're asked to use Faraday's law, it's better to split it out, as I've done up here, and just work out which one's changing and which one's not. Maybe there'll be another question we can go through just to practice that a little bit further. B. Suggest why the time taken for the whole of the coil to enter the magnetic field increases if the coil is a continuous loop. Aha! We've actually almost answered that a little bit above, haven't we? If the coil is a continuous loop, current will be induced in the coil as it falls through the magnetic field. And this is because there's a change in magnetic flux linkage. With time. So current will be induced in the coil. Due to Lenz's law, the direction of current must be so that the resulting magnetic field opposes the magnetic field causing the change. That means there'll be two opposing magnetic fields and it will slow the coil down. A bar magnet is close to a coil, no other magnetic fields are present, an ammeter is connected to the coil. We know that when there's relative motion, between magnetic field lines and a coil of wire, then EMF and current are induced. So we're looking for relative motion to make a deflection on that ammeter. The magnet and coil are both moved in the following ways. Which of the following will the ammeter indicate a current? So 1. The magnet and the coil are both moved to the right with the same speed. Well, that's not going to induce a current because there's no relative motion. If you were the magnet looking at the coil, you wouldn't see it moving because it's not moving relative to it. And if you were the coil looking at the magnet, you wouldn't see the magnet moving at that point because they're both moving at the same speed. So relative to each other, they're not moving. The magnet is stationary and the coil moves to the left. Yes, that's relative motion. The coil is stationary and the magnet moves to the right. Yeah, that's relative motion. So it's 2 and 3. The answer is C. The diagram shows a loop L of wire in a uniform magnetic field. The loop encloses an area A and the field is directed at an angle theta to the normal of the plane of the loop. The strength of B is increasing at a uniform rate R. So what that means is that dB by dt is equal to R. What is the EMF induced in L? So EMF is the rate of change of magnetic flux linkage. So d by dt in BA cos theta. We can see that N does not change, it's 1. A does not change, we're not changing the area of the coil, so that's constant. Cos theta does not change, that's constant. So if we rearrange this equation above, what we've really got is N, oh actually N is 1. We've got A cos theta, because that comes out, dB by dt, and B is the only thing that's changing. And instead of dB by dt, we put R, so EMF is equal to AR cos theta. Are there any answers there that give us that? Yep. B. A metal ring is placed in a magnetic field which is directed upwards. The magnetic flux through the ring increases over a time interval. So that means that last sentence tells us that there is a change in magnetic flux linkage with time. And according to Faraday's law, that will induce an EMF and a current. And can we induce a current? Yes, because this is a continuous loop. So a current will be induced in that coil because the magnetic flux linkage changes with time. But that's not the question. State and explain the direction of the current induced in the ring during this change. Well, this is to do with Lenz's law. Lenz's law states that the current induced must be in the direction that opposes the change that's causing it. So the change that's causing this current to be induced is upwards. So the change, well, let's put in magnetic flux linkage. That is causing the current to be induced is upwards. Therefore, the magnetic flux created by the current must be downwards, because Lenz's law states that the induced current must create a field that opposes the change that causes it. So we know that the magnetic field, resulting magnetic field from that induced current, must be downwards. So how do we work out what the direction of the current is? Well, we can use the right hand screw rule for that. And what the right hand screw rule is if you take your right hand, pop your thumb out, that's a thumb, and curl your fingers round as if you're about to punch somebody with your thumb out in your right hand. The thumb shows the direction of the current, and the fingers curl round in the direction of the magnetic field. Now, inside this coil here, our magnetic field we want to point downwards. So we want to curl our fingers on the right hand downwards inside that field. And if you curl your fingers downwards inside that coil, downwards, then your thumb will point this way. And that means that your current is clockwise. So therefore, the induced current must be clockwise. B. The following data are available. We've got the resistance, we've got initial magnetic flux and final magnetic flux. That insinuates to me that we're looking at a rate of change of magnetic flux. Let's just work that out. 2.4 times 10 to the minus 5 minus 1.2 times 10 to the minus 5 over time 2 times 10 to the minus 3. Calculate the average current induced in the ring. Well, we can't find current straight away, but we can find EMF. And if you remember correctly, I is equal to V over R, and we've got R. So let's find EMF first using Faraday's law. So it's d by dt in, which is magnetic flux linkage. How many rings are there? There is just one ring. So N is equal to 1. We're looking at d by dt B A cos theta. our B is going to change. It is dB by dt. There's no information given about area, so let's just say area equals 1. Cos theta is equal to 1 because theta equals 0. So our induced EMF is equal to the rate of change of magnetic field. And that is, if we put that into our calculator, 6 times 10 to the minus 3 volts. We don't want voltage, we want current, so I is equal to 6 times 10 to the minus 3 divided by resistance, which is 3 times 10 to minus 3, which gives us a current of 2 amps. We should probably do that to 2 significant figures, because everything else is 2 significant figures. A flat coil with N turns has a cross-sectional area of A. The coil has a flux density of B in the direction of 90% to the plane of the coil. What is the magnetic flux linkage? The magnetic flux linkage is given as this, which can be simplified down into NBA cos theta. And theta is, if that's the coil and that's the fields going through it, theta is that angle there in a direction of 90 degrees to the plane of the coil. So that means that theta is 0. So cos theta equals 1. NBA, so our answer is NBA D. I was checking out the angle there because that could have been a trick question. It could have been A if we had, if it was 90 degrees, then it would have been 0. The graph shows the variation with time of magnetic flux passing through a loop of wire. So magnetic flux, how it changes with time. How does magnetic flux change with time? What is the magnitude of the EMF induced in the coil? Well, EMF induced is defined as the rate of change of magnetic flux with time. That change does not change, it's constant. Because the rate of change, it's got a constant gradient. It's constant. So the rate of change does not change with time. So we're looking at a constant EMF. Oh, what is the magnitude of the EMF? Oh, it's the gradient. That's how it changes with time. I thought it was actually going to give us a value, but there we go. The graph shows the variation with time of the voltage output of a generator. Assuming the scales are identical, which graph shows the output when the speed of rotation is doubled? When we have a doubled speed, that means that the frequency doubles, which means the wavelength decreases by a half. So we're looking for something that shows a decreased wavelength by a half. But also what happens, that's the first thing that happens. The second thing that happens is that the EMF doubles, because you're effectively increasing the rate of change of magnetic flux by 2, which means your EMF increases by 2 as well. A uniform magnetic field directed into the page occupies a region of width L. A conducting coil of width L moves a constant speed V from left to right through the field. So there will be a current induced in here because it's a closed coil, which means we'll be dealing with Lenz's law. That means that the direction of the current will change as we go through this magnetic field. From the instant that the coil enters the field until the instant the coil leaves the field, which following best describes the direction of the current induced in the coil. So let's take the moment that the coil enters the field. We're going to use Fleming's right hand rule. So notice I'm using this hand to determine what the direction of the induced current is. So the thumb is the movement, the direction of movement. It's on the right hand. The first finger is the field, and that is into the page. And the second finger is the direction of the induced current. This is just initially, okay? So I'd like you to take your right hand I'd like you to make all your fingers perpendicular to each other. I'd like you to stick your thumb to the right in the direction of the V. I'd like you to stick your first finger into the page. And then what you'll notice is your second finger is pointing up the way. So initially, we'll have a current that's going that direction, which is anti-clockwise. Let's go down to the answers. So it's either A or C. Now, when this coil starts to leave, we have experienced Lenz's law. And what Lenz's law states that the induced current, or EMF, is in the direction of the change, is in the opposite direction of the change that causes it. So what that means is there's going to be an induced current by going through that field that opposes the current that goes in there. So as it goes through the magnetic field, it's going to change direction to be clockwise. So our answer is C. A bar magnet falls vertically from rest through a coil of wire. The potential difference across the coil is recorded by a data logger. The graph shows the variation in time PD across the coil. Well, I'm just going to try and predict what that graph looks like, if you don't mind. And we're going to talk through it just because it'll really solidify this idea of Lenz's law and Faraday's law. Let's say this is t equals 0. At t equals 0, there will be no PD across the coil. That's because it's not moving. And there is no rate of, and there's no change in magnetic flux linkage with respect to time. But after a short while, the magnet will start to move and it will accelerate. So magnet accelerates, and it accelerates at a rate due to gravity. That means due to Faraday's law, the PD, or the EMF induced, will increase. So we're looking at an increased EMF that's induced due to Faraday's law. However, as current is induced in the coil, it will create its own magnetic field around it. Lenz's law states that this magnetic field must be in the opposite direction to the one to the permanent magnet's field. And that means that the induced EMF, or PD if we're calling it in this question, is in the opposite direction. So what we're going to find is we're going to find a graph that looks like this. And PD, that's in seconds, and that's in voltage. It's going to have, I mean, it could be either way, but we could say it goes like this, suddenly, and then it goes like that. Let's see if we're right. Oh, there we go. Okay. Explain why, with reference to Faraday's law and Lenz's law, the shape of the graph. Let's go to Faraday's law first. We've actually already done this. Faraday's law. Magnet accelerates. Therefore, EMF induced increases because the rate of change of magnetic flux linkage increases. That means that so we get peak EMF. Lenz's law explains the two peaks, opposite peaks, because induced EMF or induced current must oppose the change that causes it. We could say that the second peak is higher than the first peak. Is greater than first peak because magnet accelerates. And we can also say, if you'll notice, that the first peak is just under 0.2 seconds wide, and the second peak is much less than that. So we can also say the second peak is narrower than first peak for the same reason, because the magnet accelerates. Question 2. The coil has 1,500 turns. Calculate the magnitude of the maximum rate of change of flux. Let's use Faraday's law for that. And we want to know what this value here is. That is the rate of change of magnetic flux. Remember that magnetic flux linkage is that, and magnetic flux is just that. So we want to find out what the rate of change of magnetic flux is. So we want to find out what that value there is. We know that the maximum EMF induced, if we look at the graph, it's not 0.6, it's 0.8. So we know that 0.8 equals minus n is 1,500. Rate of change of magnetic flux. So this value is equal to 0.8 divided by minus 1,500, but we don't need to take in the minus because it says magnitude. So our answer is 5.3 times 10 to the minus 4, and our units here is Webers per second, because magnetic flux is given in Webers and the rate of change of that will be per second. I'm going to stop there because I don't know if you noticed, but my pen is starting to lose battery. Also, I think we've done quite a long time. So I'm going to stop. I hope that's been useful. In particular, what's really shining through is that they're constantly asking you to explain the change in a direction of current due to Lenz's law. So I'd be really happy with that. And the other thing that they ask you to do in an extended question is use Faraday's law to calculate the EMF induced. So you have to get quite good at recognising what is actually changing to cause that EMF to be induced as part of Faraday's law.